Assalamualaikum and selamat sejahtera. My name is Muhammad Yusuf bin Ismail. My student ID is AN180025. My research title is Bioethanol Production from Palm Oil Empty Fruit Bunch using Simultaneous Saccarification and Fermentation Process. My supervisor is Dr. Eliza binti Muhammad and my co-supervisor is Technologist Dr. Hanis Hayati binti Hairum and Madam Siti Fatimah Muhammad Noor. Malaysia, as a world second biggest palm oil producer, have abundant biomass resources such as palm oil empty fruit bunch derived from palm oil plantation waste. When palm oil empty fruit bunch are abundant, it have high potential to convert into ethanol by using simultaneous saccarification and fermentation process. The investigation on the influence of treatment, pre-treatment condition and yeast loading in SSF process, as well as analysis on glucose concentration in SSF during using dinitrosalicylic acid method were done in this study. The study will dry, cut, sieve palm oil empty fruit bunches to reach specific particle sizes. Then, the palm oil empty fruit bunches are pre-treated chemically or hydrothermally. Thermogravimetric analysis will be used to acquire the cellulose and lignin content of each palm oil empty fruit bunch, and the result will be reported as proximate analysis. Then, by changing the pre-treatment condition as well as the dry yeast loading, we were able to do simultaneous saccarification and fermentation process. The extracted ethanol content using the rotary evaporator will be analyzed using the GCFID. The ethanol presents in the sample with 30 to 120 minutes retention time of chemical and hydrothermal treatment by 1 to 5% yeast loading is 72.68 mg per ml, 64.88 mg per ml, and 64.37 mg per ml, while the ethanol presents in the sample with chemical treatment by yeast loading 1 to 5% is 62.45 mg per ml, 60 and 60.6 mg per ml. As a conclusion, all of the objective of this study was successfully achieved, and bioethanol production from POEFB using SSF process was successfully produced and evaluated. For the introduction, firstly, Malaysia is one of the largest and important country in Southeast Asia for the growing economies in oil palm industry. Oil palm biomass is the alternative and promising renewable energy due to the increasing price of crude oil nowadays. Basically, the bioethanol produced from the lignocellulosic biomass requires 4 main steps, which are the physical and chemical pre-treatment of the lignocellulosic biomass that contains in palm oil empty fruit bunch as their first step. Next, enzymatic hydrolysis of cellulose to sugars as their second step, fermentation of the resulting sugars from the second step as their third step, and finally, it will undergo the extraction of ethanol. For the literature review, firstly is renewable energy. It is a sustainable renewable energy pertains to the generation of energy from sources that are sustainably producing resources within the human time scale. That is, energy resources that can be replenished without concern for degenerative capacities. Hydropower, biomass, biofuel, geothermal energy, solar energy, and wind energy are the example of the renewable energy. Secondly, bioethanol from palm oil empty fruit bunch. There is a wide possibility for repurposing waste palm oils into renewable energy supplies that might fulfill current demand for energy from palm oil factories or from other sectors and enhance sustainability in the palm oil sector. Thirdly, simultaneous saccarification and fermentation. It is the main objective utilization of the enzyme hydrolysis and fermentation process is to decrease end product inhibition of enzyme hydrolysis and to decrease investment costs instead of in a separate stage following hydrolysis. The key disadvantages are, however, that both enzymatic hydrolysis and fermentation must be favored, and that the fermenting organism and enzyme can be hardly recycled. For the methodology, firstly, raw material processing and pre-treatment. The palm oil empty fruit bunch was dry at 105 degrees Celsius for 8 hours and was shredded to 2 mm size. Then, the shredded palm oil empty fruit bunch was submerged in 0.3 mol sodium hydroxide solution for 4 hours. Then, the material was exploded in pressure cooker with different time range. Second, after that, raw material characterization. The cellulose and lignin content were obtained from both treatment by using thermogravimetric analyzer equipment with ramping rate 10 degrees Celsius per minute, max temperature 700 degrees Celsius and gas flow rate at 21 ml per minute. Thirdly, the preparation of 0.05 molar citrate buffer with pH 4.8, 4.5 to 9 gram of nitric acid and 7.771 gram of sodium citrate dehydrate were added to 800 ml distilled water. Hydrochloric and sodium hydroxide were used to adjust the final desired pH 4.8. Fourthly, dinitrosalicylic acid reagent solution preparation. 1 to 3 grams of 3,5-dinitrosalicylic acid, 1.6 grams sodium hydroxide were added to a beaker containing 60 ml water. Over 20 minute duration, 30 grams of potassium titrate were applied and stir it slowly. Fifthly, we proceed to the experiment of simultaneous saccharification and fermentation process. The produced POFB was autoclaved, sterilized at 121 degrees Celsius for 120 minutes in 150 ml of 0.05 molar buffer citrate pH 4.8 in an aluminium flask. Then add 1% gram per ml Saccharomyces cerevisiae, which is dry yeast, and 0.5% enzyme solution. A 72 hours process was carried out in a shaken incubator at 32 degrees Celsius with 150 rpm agitation. The calibration graph and the equation obtained from the graph is y is equal to 0.065x plus 0.3198. For the bioethanol extraction by using rotary evaporator, the rotary evaporator equipment was set up with correct adjustment. Select the ethanol solvent at the solvent library with bath temperature 42 degrees Celsius. Boiling point is 20 degrees Celsius and the pressure is 58 mbar. For the final step, bioethanol analysis by using gas chromatography fluid ionization detection. 1800 microliter of 1-propanol as a solvent were added to 200 microliters of sample after ethanol extraction using a rotary evaporator. The vial was crimped shut and placed on the instrument. Repeat 5 more times with the same step. All samples were tested at 40 degrees Celsius initial headspace and 250 degrees Celsius maximum oven temperature. The vial equilibration time was set to 16 minutes and the vial pressurization at 13.998 psi. For the result and discussion, firstly, palm oil empty fruit bunch characterization. 2 samples were analyzed for thermogravimetric analysis (TGA analysis). 1 sample had undergone chemical treatment only. Another sample had undergone both chemical and hydrothermal treatment. Table 1 shows the cellulose and lignin content in samples by each pre-treatment method. Raw palm oil empty fruit bunch has 41.3 to 45% cellulose, 25.3 till 33.8% hemicellulose, and 27.6 to 32.7% lignin. The explosive effect on the biomass is due to the removal of hemicellulose from biomass during hydrothermal treatment and liquid hot water pretreatment. Table 1 shows that using combined chemical and hydrothermal treatment enhances the percentage of cellulose much more than using simply chemical treatment. Comparing sample with any without chemical treatment lower the proportion of lignin. The higher percentage of cellulose in samples treated both chemically and hydrothermally was due to the hydrothermal treatment itself. Solubilization increased as pre-treatment substances worsened in general. More severe hydrothermal treatment condition resulted in increased solubilization of the cellulose fraction. Table 1 shows the cellulose and lignin content in sample by each pre-treatment method. For the chemical pre-treatment only, the cellulose content is 55.767%, while the lignin content is 27.266%. And for the cellulose content in the chemical and hydrothermal treatment is 57.707%, while the lignin content is 25.395%. For the simultaneous saccharification and fermentation study, to evaluate the influence of retention time, each sample adsorbent was measured and its glucose content was determined using equation 3.1. Figure 3.5 shows the effect of hydrothermal treatment retention time on glucose concentration. Figure 5 shows that the sugar concentration increased as the hydrothermal treatment condition got more severe. The severe condition, which is longer retention time in hydrothermal treatment, dissolve more hemicellulose, increasing enzyme accessibility to cellulose, and as a result, more glucose was generated after the enzymatic hydrolysis. For the effect of dry yeast loading, yeast can directly ferment simple sugars into ethanol, but other sort of feedstock must be transformed to fermentable sugars before it can be fermented to ethanol. It is suggested that the limited amount of sugar recovered from sugarcane-based gas could be the explanation for high level of ethanol concentration. From figure 7, it can be shown that the higher yeast loading in sample leads in lower glucose concentration, either in different retention time in hydrothermal treatment or in chemical treatment only. It was because numerous glucose had previously converted into ethanol by each rise in percentage of yeast loading. For the analyzation of bioethanol content, the number of peaks present indicate three components present in the mixture. The x-axis of the chromatogram shows the amount of time taken for the analytes to pass through the column and reach the FID detector. The y-axis, or the area of the peak, is a reflection of the amount of a specific analyte that presents. Previously, the graph result of ethanol content had been simplified and written into Table 2. Table 2 shows ethanol content in each example. For the first graph, ethanol content in sample with 120 minutes retention time, which is in chemical and hydrothermal treatment by 1% yeast loading. Based on the graph, the highest peak area of the graph is at the 2.86 minute of retention time with 39.05 PAS of PA value at y-axis. Therefore, the amount of ethanol present in the sample with 120 minutes retention time of chemical and hydrothermal treatment by 1% yeast loading is 72.68 mg per mil. For the second graph, it is the ethanol content in sample with 60 minutes retention time, chemical and hydrothermal treatment only by 3% yeast loading. The graph illustrated the highest peak area of the graph is at the 2.86 minute of retention time with 34.84 PAS of PA value at y-axis. Therefore, the amount of ethanol present in the sample with 60 minutes retention time of chemical and hydrothermal treatment by 3% yeast loading is 64.88 mg per mil. For the third graph, ethanol content in sample with 30 minutes retention time from chemical and hydrothermal treatment by 5% yeast loading. Based on the graph, the highest peak area of the graph is at the 2.86 minute of retention time with 34.56 PAS of PA value at y-axis. Therefore, the amount of ethanol present in the sample with 30 minutes retention time of chemical and hydrothermal treatment by 5% yeast loading is 64.37 mg per mil. For the fourth graph, ethanol content in sample with chemical treatment by 1% yeast loading. The graph illustrated the highest peak area of the graph is at the 2.86 minute of retention time with 33.53 PAS of PA value at y-axis. Therefore, the amount of ethanol present in the sample with chemical treatment by 1% yeast loading is 64.45 mg per mil. For the graph number 5, ethanol content in sample with chemical treatment only by 3% yeast loading. The graph illustrated the highest peak area of the graph is at 2.86 minute of retention time with 32.53 PAS of PA value at y-axis. Therefore, the amount of ethanol present in the sample with chemical treatment by 3% yeast loading is 60.6 mg per mil. For the last graph, which is the sixth graph, is the ethanol content in sample with chemical treatment only by 5% yeast loading. The graph illustrated the highest peak area of the graph is at the 2.86 minute of retention time with 32.53 PAS of PA value at y-axis. Therefore, the amount of ethanol present in the sample with chemical treatment by 5% yeast loading is 60.6 mg per mil. In this study, bioethanol was successfully produced from the palm oil empty fruit bunch as a raw material by using SSF method. Therefore, the amount of ethanol present in the sample with 120 minutes retention time of chemical and hydrothermal treatment by 1% yeast loading is 72.68 mg per mil. This sample contains the highest bioethanol produced compared to other samples with different retention time in hydrothermal treatment and different yeast loading. In conclusion, the present study has successfully produced the bioethanol from palm oil empty fruit bunches using simultaneous saccharification and fermentation technique. Last but not least, the ethanol present in the sample with 30 to 120 minutes retention time of chemical and hydrothermal treatment by 1 to 5% yeast loading is 72.68 mg per mil, 64.88 mg per mil and 64.37 mg per mil, while the ethanol present in the sample with chemical treatment by yeast loading, which is 1 to 5% yeast loading, is 62.45 mg per mil and 60.6 mg per mil. However, all the objectives in this study were successfully achieved. These are the examples of the reference used in this research. Thank you, and that's all from me.